So thank you very much, and good afternoon. So I would like to introduce you to the practices that are emerging in Malta towards smart buildings. Before that, I want to take you a few years back, though, because I picked these examples because they tie in the architecture, the local architecture perhaps, with the environmental strategy that was adopted in these buildings. So I think it's a good example to start off with, because it's something that is a starting point for smart buildings, in my opinion. The buildings on the left are forming part of a brewery. The architecture of the building and the form of the building is reflecting the environmental strategy that was adopted in that building. They both use buoyancy-driven natural ventilation and the thermal mass of the building to provide natural cooling. On the right, a very different situation, which we often face in Malta. It's the Malta Stock Exchange, which is housed in a 19th century garrison chapel. So in this case, the priority of the team was that of respecting the architectural qualities of the building. So the intervention and the building services had to be less intrusive as much as possible. So in this case, a passive downdraft evaporative cooling system was used, assisted with cooling coils and also night ventilation similar to the other buildings. Possibly something to learn, the bit of a downfall of this project was that the building was occupied before the system was fully commissioned, so there were some issues which could easily be resolved. However, the occupants were already in the building, so they kind of associated certain problems with the system, whereas it could have been easily modified. What we are doing today, this is the Parliament building, which was constructed and completed recently. The key sustainability principles for this project were very important, and they follow the definition of energy, which is power times time. So in this case, the team focused on the passive design strategies, energy efficiency, and reducing the demand. In this case, the architecture is also very closely linked with some of the environmental systems that were installed. So the building is a heavy mass. It is clad in stone throughout on the exterior and some parts also on the interior to assist with the thermal mass. The skin of the building is a stone cladding, which has been sculpted to appear as though the stone has been eroded. And this forms the shading for the building and also lets natural light within the building and views from inside the building to the outside. In terms of energy systems, we're using LED lights with presence detection. In the Parliament chamber and the ground floor levels, we're using low energy, low pressure displacement systems for ventilation, heating, and for cooling. We've installed ground source heat pumps to assist with the heating and the cooling, PV panels on the roofs for energy generation, and collecting rainwater for second-class water to reduce the load on our reverse osmosis plants. This is a schematic of the building, just to help you understand how it's working. The building is situated on a tunnel, on an old tunnel, which is accommodating the plant and sitting on rock. So we're making use of the rock as a heat sink for the ground source heat pumps. So around 30 boreholes which were drilled around 150 meters within the rock. And the system, it's a closed loop system with water circulating within the boreholes. In the summer, the water which circulates into the boreholes is at a warmer temperature, but returns at a lower temperature, so assists with the cooling. And in the winter, the water is at a lower temperature and returns at a temperature of around 21 degrees, so covering most of the heating demand. The building is used intermittently, and some of the use patterns were very difficult to predict, so energy reduction was very important. So some of the rooms, most of the rooms have presence detection, so the systems turn on when the space is in use and turn off when it's not in use. There is CO2 monitoring so that the ventilation is kept to a minimum, and people are encouraged to open windows for natural ventilation, so when the windows are open, the systems turn off automatically. So the building is currently being monitored. There is a metering of the plants to be able to check the usage. controlling the temperatures, monitoring the temperature and relative humidity to be able to evaluate the way it's performing and optimize it. This is another example, very different from the previous ones. It's a research project, and it's also a retrofit. And this is a pilot project, so the idea is to develop and understand which energy efficient measures are more effective, which are more cost effective to assist us in retrofitting of other school buildings. The aim is also to improve the thermal and visual environment and obviously reduce the energy consumption. This is a layout of the school, so there's a central yard with classrooms and corridor along the perimeter, which is very typical construction locally. So some of the measures that were introduced was shading. Of course, in Malta it's hot, so shading is very important. The corridors were originally left open, but now with time they have been closed to reduce the problem of rain entering the classrooms and keep the space cleaner. So this results in a lot of heat gain within these corridors and then into the classrooms. These vertical louvers have been introduced on the east and west facing windows, which are connected to a building management system and automated depending on the amount of solar radiation and the internal temperatures. We also introduced fixed overhangs on the south facade, which is easier to shade, and we accommodate PV panels and solar thermal tubes to generate energy. So this is something very local where we often use natural ventilation. We don't often have cooling in schools. And in fact, in this case, the heating system was by portable electric heaters. So we replaced these electric heaters with infrared panels, which are far more efficient. The occupant can decide when to turn it on or off, but the building management system controls the temperature. All the lights were replaced with energy-efficient lights and with occupancy sensors and light dimming in some of the classrooms. So as I said, the ventilation is generally natural ventilation. So that contributed to significant losses in winter. The team suggested to introduce mechanical ventilation. The occupants were not very happy about this change at the beginning. However, the CO2, the ventilation is CO2 driven, depending on the amount of CO2. So having the teacher understand what the monitor is telling the teacher gave her and them more confidence in the system. So they are very happy to use it now. So this reduced considerably the energy losses. It also was used for night cooling. So this is a scenario before the building was retrofitted with a corridor along the perimeter facing the courtyard. During the studies, it was observed that within the corridor, the temperatures were higher than the temperatures in the classroom because they were being passively heated because of the large glazed areas. So the corridor was used as a way of pre-warming the air for natural ventilation, for mechanical ventilation, sorry. And an inlet grill was inserted between the corridor and the classroom and an exhaust air between the classroom and the street. So it's a very simple system, but thanks to the natural heating of the space can be used effectively. More PV panels were inserted on the roof. There's also a pool, which is used throughout the year, and the solar thermal absorbers, which are located over the shading structure, is being used with heat pumps for heating of the pool. And an automated polycarbonate cover was introduced on top of the pool to be able to reduce evaporative losses. The result of having all these measures together with the building management system was that the building is consuming zero energy. This is obviously based on a 1 year, so it needs to be monitored further, optimized, and hopefully find a better way to be able to replicate this into other schools at a more affordable cost. What are we doing now? Where are we heading? So leaders in energy management field are focusing on how can we translate data into information more effectively and give it to the right person at the right time. Architects and building services engineers are also focusing more on automation and building management and introducing those more into building to reduce the demand. From an academic point of view, we are looking into sensors for performance of the building envelope. We're looking at the benefits of automation and building management in smaller scale buildings as well. So how can it work in a household and how can it be beneficial in a household? And we're looking into how can we implement zero energy, zero carbon buildings locally. So thank you. If there are any questions, feel free to ask during the Q&A. Hope you enjoyed the presentation.